Welcome to our latest video on making salts from acids and alkalis, titrations. This video is suitable for GCSE students. By the end of this video lesson, you should understand that when an acid is reacted with an alkali, a salt and water is formed in a neutralisation reaction. You should also be able to explain how crystals of soluble salts can be prepared from the reaction of an acid and an alkali via the titration method, and finally should be able to name the salts formed and be able to write word equations to describe these reactions. Now, in our previous video lessons, we've learnt that the chemical opposites of an acid are called bases, and a base is any metal oxide or hydroxide. So for example, copper oxide is classed as a base because it's a metal oxide. Magnesium hydroxide is also classed as a base because it's a metal hydroxide, and any base that dissolves in water is classed as an alkali. So alkalis are just bases that are soluble. Now, alkalis can be described as substances that split up into OH- ions when you put them in water. So for example, sodium hydroxide is NaOH, and when you put that in water it splits up into Na+ ions and OH- ions. And you remember from previous lessons that acids are substances that split up into H+ ions when you put them in water. Now, in a neutralisation reaction, H+ ions from acids react with OH- ions from alkalis to form water. Now, neutralisation reactions are also exothermic because during these reactions heat is given out to the surroundings, and this leads to a temperature rise. Now, at GCSE, the alkalis that we come across are lithium hydroxide, sodium hydroxide, potassium hydroxide and ammonium hydroxide. And the chemical formula of lithium hydroxide is LiOH, sodium hydroxide NaOH, potassium hydroxide KOH and ammonium hydroxide NH4OH. Now, at GCSE, we learn about the different groups in the periodic table, and group 1 in the periodic table is called the alkali metals, and this is because when you put group 1 elements in water, they react violently and form metal hydroxides and hydrogen gas, and the metal hydroxides that form are soluble bases, they're alkalis, and that's why the group is called alkali metals. In our previous lessons, we've learnt that salts are chemicals made from acids, and in a salt, the hydrogen atoms in the acid are replaced by metal atoms. So for example, hydrochloric acid is the chemical formula HCl, sodium chloride is a salt made from hydrochloric acid and has the chemical formula NaCl. The hydrogen in hydrochloric acid has been replaced by metal atoms, in this case sodium, and that's why sodium chloride is classed as a salt. Salts made from sulfuric acid are sulfates. So for example, magnesium sulfate has the chemical formula MgSO4, and we've replaced the hydrogen in sulfuric acid by magnesium. Nitric acid has the chemical formula HNO3, and its salts are nitrates. So for example, potassium nitrate has the chemical formula KNO3, and we've replaced the hydrogen in nitric acid with potassium atoms. Now, in our previous lessons, we've learnt that a salt can be made by adding an acid and an insoluble base together. Now, when an acid and a base react together, they form a salt and water. And in previous lessons, we've seen that salts such as copper sulfate can be formed by this method. If we take sulfuric acid and add an insoluble base, copper oxide, and warm the mixture, we can then filter off any unreacted copper oxide, and the soluble salt that forms, copper sulfate, can then be heated in an evaporating basin to remove the water to leave crystals of the soluble salt. And we've studied this in detail, and the word equation shows that if you add copper oxide to sulfuric acid, you make copper sulfate and water. And that is an acid reacting with a base to form a salt and water. Now, an advantage of this method is we don't have to measure the volume of acid out accurately, and we don't have to measure the mass of base accurately either, because all we have to do is add enough base to neutralize the acid. Now, this is achieved by adding the base until it stops reacting and forming a soluble salt. So when you add copper oxide, which is an insoluble base, to sulfuric acid, the copper oxide disappears. It's not dissolving, it's forming a new substance, copper sulfate, which is soluble, and that's why it disappears. Now you keep adding the copper oxide until it stops disappearing. And when it stops disappearing, the reaction is over, the acid has been neutralized, and you see the copper oxide appearing in the beaker. Then all you have to do is filter the unreacted or excess copper oxide to leave your soluble salt, and the solution of your soluble salt is heated to form crystals of your soluble salt. So that's the big advantage of this method. You don't have to measure the volume of acid or the mass of base out accurately. Now, alkalis are just soluble bases. So when you react an acid and alkali together, you also get a salt and water. So for example, hydrochloric acid is an acid, you react it with the alkali sodium hydroxide, you form the salt, sodium chloride, and water. Now we can also describe this reaction with a chemical equation. So the formula of hydrochloric acid is HCl, the formula of sodium hydroxide is NaOH, sodium chloride has a chemical formula NaCl, and water's chemical formula is H2O. So HCl plus NaOH makes NaCl plus H2O. Now the problem of using an acid and an alkali to make a soluble salt is that we need to be very exact in terms of the volumes of acid and alkali that we add. The acid and alkali are both liquids, and we need the exact amount of acid to neutralize the alkali and vice versa. And this is achieved in a method called a titration. And in this video we're going to look at the titration method in detail. Now when carrying out a titration, we need to be able to measure out very accurate volumes of acid and alkali, because remember we need the exact amounts of each to neutralize each other. Therefore we use accurate measuring equipment called a burette and a pipette. And burettes and pipettes allow us to measure the volume much more accurately than a measuring cylinder. And this slide shows pictures of a pipette and a burette. And it's important that you can recognize these in exam questions. Now this slide shows a summary of the main steps for carrying out a titration. Now the first step is to put a known volume of acid or alkali into a conical flask. Now a pipette is used to accurately measure this volume of acid or alkali. And in this picture you can see that we've used the pipette to measure the volume of alkali accurately, and we put the alkali into the conical flask. Now there are different sizes of pipettes, but usually in a titration the pipettes that we use will measure out either 20 centimeters cubed of alkali or acid or 25 centimeters cubed of the acid or alkali, and they will measure this out accurately. And in this picture you can see that we put the alkali into the conical flask. Now the next step is to add indicator. Now in titrations we use indicators that are one colour in acid and another colour in alkali. So universal indicator would not be appropriate here because we get a range of colours, and we just need an indicator that is one colour in acid or one colour in alkali. So litmus would be an appropriate indicator here because litmus would go blue in alkali and would be red in acid. Now, when carrying out a titration, there are lots of indicators that chemists will use, and one popular indicator is an indicator called phenolphthalein. And phenolphthalein is pink in alkaline solutions and colourless in acidic solutions. So after I've added my indicator to the alkali that's in my conical flask, I fill up my burette with the acid I'm going to use, and I note the initial volume in the burette. Now the burette has volume markings on it, and I can read off the starting or initial volume. And then I add my acid to my alkali and indicator, swirl in my flask until the indicator changes colour. And when the indicator changes colour, I know that my alkali has been neutralised. And I note the final reading or volume of acid in my burette, and I work out the volume of acid that I've added that was needed to neutralise my alkali. Now in a titration, we use the indicator to find the exact volume of acid needed to neutralise a known volume of alkali, or vice versa, because we could put the acid in the conical flask and put the alkali in the burette. Now once we know this from our experiment, all we would need to do is repeat the experiment without the indicator, adding the exact volume of acid or alkali needed for neutralisation. And once we've done this, all we would then do is evaporate off the water to form crystals of our soluble salt. Now because we're looking for the exact volume of acid needed to neutralise the alkali, titrations are often carried out a number of times with indicator until we get values that are consistent, in other words, volumes that are close together. When we have consistency in the volumes of acid needed to neutralise the alkali, chemists will take an average volume or titer, and then they will use this without the indicator to form the soluble salt. So now let's see a titration being carried out. So in the next video clip, we see my colleague Mr. Firth making the salt sodium chloride. So he's going to fill up his burette here with hydrochloric acid, because that's the acid you need to make sodium chloride, and he measures the initial volume or starting volume of acid in the burette. Now the next thing that Mr. Firth does is he uses a pipette to measure out a known volume of alkali, in this case sodium hydroxide, because we're trying to make the salt sodium chloride. So he uses his pipette to measure out 25 centimeters cubed of the sodium hydroxide, and then he's going to add his indicator. Now the alkali and indicator are placed in a conical flask, and you can see that the indicator has changed the solution to pink, and that's because we've used the indicator phenolphthalein, and that indicator is pink in alkaline solutions and colourless in acidic solutions. So Mr. Firth then adds the acid carefully using a burette. So to do this, he's just opened up the tap and he's adding the acid from the burette to the alkali and indicator, and he's swirling the flask to make sure that the acid is fully mixing with the alkali and the indicator. Now Mr. Firth is carefully adding the acid, and he's going to add the acid until the indicator changes colour. Now as he carries out the experiment, you can see that the indicator is starting to lose its pink colour, and this is indicating they're getting close to what we call the end point, the point of neutralisation. Now Mr. Firth is making sure here, by using some deionized water, that the acid and alkali is actually in the conical flask and not on the sides of the flask. He's rinsing it with some water. And he's just added one more drop just to make sure that he's ended up with his colourless solution and he's reached the end point. Now all Mr. Firth will then do is note the final reading. So you can see that the final volume here is 20.00 centimetres cubed, and his initial volume was 1.40 centimetres cubed. So to find the volume of acid that he's added, all you do is take the initial volume, 1.40, away from the final volume, 20.00. And you can see that he's added 18.60 centimetres cubed of acid. That was the volume of acid needed to neutralise the sodium hydroxide. Now when carrying out a titration, the first experiment is often considered a rough experiment, because in this experiment you have no idea how much acid or alkali is needed to reach the end point or neutralisation point. So this first experiment has given Mr. Firth a rough idea of the volume of acid that he needed to neutralise his 25 centimetres cubed of NaOH, sodium hydroxide. So if Mr. Firth completes further experiments, further titrations, when he gets close to adding 18.60 centimetres cubed, he can be extra careful to make sure that he doesn't miss the end point, and he would add the acid drop by drop as he approaches this 18.60 volume. Now you can see from these results that Mr. Firth carried out two further experiments here, and in both these experiments the volume of acid needed to neutralise the sodium hydroxide was 18.40 centimetres cubed. Now notice, when carrying out these two other experiments, Mr. Firth didn't have an initial reading or volume of 1.40 centimetres cubed, because that's not needed, because all you need to do is note your initial volume of acid in the burette, note your final volume of acid in the burette after you've added it to the alkali, and do the final volume minus the initial volume to work out the volume of acid added. So in both these cases, the volume of acid added was 18.40 centimetres cubed. Now Mr. Firth has decided that experiment 1 was a rough experiment, so therefore he's calculated an average titer based on experiment 2 and experiment 3, and that is common for chemists to do that. Now at GCSE, you might come across questions where all the values that they give you are very close together. They're all within, say, 0.2 centimetres cubed of each other, and you can average all three of them to find your mean titer. Now when carrying out a titration, we're looking for consistent values. We're looking to achieve titer values within 0.2 centimetres cubed of each other, and ideally within 0.1 centimetres cubed of each other. Now this is because a burette and a pipette can measure out the volume of a liquid to high levels of accuracy. Now from this experiment, Mr. Firth knows that he needs 18.40 centimetres cubed of hydrochloric acid to neutralise 25 centimetres cubed of sodium hydroxide. So if he wants to make crystals of sodium chloride, he needs to repeat the experiment again, but this time without indicator. So Mr. Firth uses his pipette to measure out 25 centimeters cubed of alkali, and then he adds 18.4 centimeters cubed of hydrochloric acid carefully using a burette. Now once he's done this and his solution is fully mixed, he pours the solution into an evaporating basin, and then he just heats up the evaporating basin containing the solution of the soluble salt sodium chloride to evaporate off the water. And when you do this, you'll be left with sodium chloride crystals. Now, like we've done in previous video lessons, we could just evaporate around about 2/3 of the water using a Bunsen and leave the other 1/3 of the water to evaporate slowly over a few days by putting the evaporating basin on a windowsill. Now in this video lesson, we've seen that the titration method can be used to prepare crystals of soluble salts from the reactions of acids with alkalis. Now in addition to this, titrations can also be used to find the concentrations of solutions of acids and alkalis, and this will be covered in much more detail in later video lessons. So now let's test your understanding of what we've covered so far with some practice questions. Read through the questions, pause the video, have a go at them, and then we'll go through the answers. So now let's go for the answers to the first practice questions. So it says a group of students were asked to find the volume of hydrochloric acid solution needed to neutralise 25 centimeters cubed of sodium hydroxide, and they decided to titrate sodium hydroxide with hydrochloric acid. And the results of the experiment as shown here on this slide. Now the first question is asking you to name the piece of apparatus X. So X is a pipette, 1 mark for that. And then part 2 is asking you to explain the purpose of the indicator. Well, the indicator helps you identify the endpoint, you could say that, or you could say that it identifies when neutralisation has taken place, or you could say it identifies when all the alkali has been used up. Any of those would get you 1 mark. So here's the next 2 parts of question 1. So once again, read through the questions, pause the video, have a go at them, and then we'll go for the answers. So part 3 is asking you to calculate the mean volume of hydrochloric acid needed to neutralise 25 centimeters cubed of the sodium hydroxide solution. So there's 2 possible approaches here and 2 possible answers that they would accept. So you could either include all 3 experimental values here. So therefore you would add 18.2 plus 17.8 plus 18.0 and divide by 3 because you have 3 experimental values. And that would give you a mean volume of 18.0 centimeters cubed. Now the second way of doing this question is to consider the first value, 18.2, as a rough value because it was the first experimental value and it's higher than the other 2. So you could consider that you may have overshot the endpoint with this first experiment. So if you ignore the 18.2 value, you would just use the other 2 consistent values, 17.8 and 18.0, to calculate your mean volume. So here it would be 17.8 plus 18.0 divided by 2, which would give you a mean value of 17.9 centimeters cubed. And that would also be accepted. Now in part 4, you're being asked the following. The experiment was repeated using hydrochloric acid of half the original concentration. And the question is asking you to state the volume of hydrochloric acid that would be needed to change the indicated colour. Now if your acid was half the original concentration, you would therefore need double the volume of this acid to neutralise the alkali. So all you need to do is double your answer to part 3. So therefore, if you had an answer of 18.0, you would need 36.0 centimeters cubed of hydrochloric acid to neutralise the alkali. Now if you had a volume of 17.9 in part 3, you would just double that, which would give you a volume of 35.8 centimeters cubed. So here's our second practice question, which we'd like you to have a go at. So read for the question, pause the video, have a go at it, and then we'll go for the answers. Now this question is asking you to explain how you would obtain crystals of the soluble salt potassium chloride, and in the question they made it clear they wanted you to use the alkali potassium hydroxide and they wanted you to use the acid hydrochloric acid. So you therefore need to explain how you would carry out a titration to do this. So step one would be to use a pipette to measure a known volume of alkali. So usually this is 25 centimeters cubed, but it could be 20 centimeters cubed. And you use the pipette to measure this out accurately, and you place the alkali into a conical flask. Now I could decide to put the acid in the conical flask. That's entirely up to you, but usually we put the alkali in the conical flask. Step 2 would be to add indicator to this. So this could be phenolphthalein, the indicator we used in the video. You then fill up your burette with acid, if you decided to put the alkali in the conical flask, and you note the initial volume. You then add the acid carefully to the conical flask of alkali, an indicator, and you swirl this until the colour changes. And that's because the end point is reached when the indicator changes colour. Now when the indicator changes colour, you note the final volume of acid in the burette, and you use this to work out the volume of acid that you've added to the alkali. Once you know this, you could repeat this several times to make sure that you've got consistent values for this volume, and then you need to repeat the whole experiment without the indicator, adding the recorded volume of acid. So for example, if you needed 18.5 centimeters cubed to neutralize the alkali, you would add the 18.5 without the indicator. You then need to say in your answer that you need to heat up the soluble salt that you've formed in an evaporating basin, because you're trying to boil off some of the water, and you leave the solution to evaporate for a few days to obtain dry crystals. Now the salt that would form would be potassium chloride, because you used potassium hydroxide and hydrochloric acid. Now the way this question was marked was, if you constructed a very articulate account and you linked virtually all these points together, you would get between 5 or 6 marks. And if you linked some of these points together, but there were a few omissions, you get 3 or 4 marks. And if you had some relevant points, but there were lots of omissions from the key content that I've pointed out here on this slide, you would get between 1 or 2 marks. So here's our last practice question. So once again, read for the question, pause the video, have a go at it, and then we'll go for the answers. So question 3 is asking you to write word equations to describe the following reactions. So if you react sulfuric acid and sodium hydroxide together, you would get sodium sulfate and water, because sulfuric acid produces sulfates as salts, and you've got sodium hydroxide. So the equation would be sulfuric acid plus sodium hydroxide makes sodium sulfate and water. Now for part B, you've got nitric acid and lithium hydroxide. So the equation would be nitric acid plus lithium hydroxide would make the salt lithium nitrate plus water. And this is because when you have nitric acid, the salt that forms is a nitrate, and the alkali here is lithium hydroxide, so therefore it's lithium nitrate. And for question C, we have sulfuric acid and ammonium hydroxide. So the salt would be a sulfate because it's sulfuric acid, and it's ammonium sulfate because we have ammonium hydroxide. So the equation would be sulfuric acid plus ammonium hydroxide makes ammonium sulfate plus water. Now this is a 3-mark question, and there's 1 mark for each correct word equation. So that concludes this video lesson. So after watching this video, you should now understand that when an acid is reacted with an alkali, a salt and water is formed in a neutralisation reaction. You should be able to explain how crystals of soluble salts can be prepared from the reaction of an acid and an alkali via the titration method. And finally, you should be able to name the salts formed and be able to write word equations to describe these reactions. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @Radachemistry.